Today, we're going to talk about something that's, well, it's basically an unbreakable law of the digital world. It's this hidden rule that governs pretty much every single online service you use, from your bank account to your social media feed. And here's the kicker. It forces all of them to make a really, really tough choice.
So let's just jump right into the big question here, the one that every massive system has to deal with. Why can't an app be perfect, like totally consistent, and be online all the time, especially when things start to go wrong? I mean, you'd think we could have both, right? But as you're about to see, reality is, well, it's just a lot messier than that.
And the reason for that messiness? It's something called the CAP Theorem. Now, this isn't some friendly suggestion or a best practice. Nope. This is a cold, hard, proven mathematical law. It was first put forward by a guy named Eric Brewer way back in 2000, and it basically sets the absolute limits for what you can and can't do when you're building a system that's spread out over a bunch of different computers.
Okay, so Section 1, decoding C, A, and P. The whole thing really boils down to understanding what those three letters stand for. C is for consistency, A is for availability, and P is for partition tolerance. So let's break them down one by one.
All right, first up, C for consistency. In the world of the CAP theorem, this is super specific. It means that everybody, no matter where they are, sees the exact same data at the exact same time. So think about it. If I update my profile picture, you see the new one right away, not the old one from 5 minutes ago. The whole system has to act like there's only one single source of truth. Now here's something that trips up a lot of people, so it's really important to get this straight. The C in CAP is not the same as the C you might have heard of in ACID databases. They're totally different things. The CAP C is all about timing, making sure everyone sees the latest data. The ACID C is about data correctness, following the rules, like making sure your bank balance can't just go into the negative without a proper transaction. Same letter, but a world of difference in what they actually mean. Okay, next up is A for availability. And this one's pretty straightforward. It's basically a promise from the system that if you ask it for something, it's going to give you an answer every single time. No waiting forever, no annoying error messages. It just responds. Now, it might not be the absolute latest piece of information, but it guarantees you'll get something back.
And that brings us to P, partition tolerance. And this, my friends, is where we hit the harsh reality of how the internet actually works. A partition is just a fancy way of saying the network connection between two parts of a system breaks. And let's be real, networks are not reliable. They fail all the time. Messages get dropped, cables get cut, servers go offline. So partition tolerance means your system has to be able to handle this chaos and keep on chugging. It's not an if, it's a when.
All right, Section 2, the fork in the road. So now that we know what C, A, and P are, let's get to the heart of it. Why on earth can't you have all three? Well, it all comes down to what happens the moment that network partition we just talked about actually happens.
This little thought experiment is basically the proof of the whole theorem. So picture this. You've got two servers, let's call them G1 and G2. They're supposed to have the exact same data. But then, bam, the network connection between them breaks. They can't talk to each other anymore. Now, a user comes along and writes some new information to G1. To stay available, G1 has to say, okay, got it, and save that new data. But a second later, another user asks G2 for that same information. Now, what does G2 do? It's completely trapped. It can either give back the old stale data it has, which means it's no longer consistent, or it can throw up an error and say, sorry, I can't answer right now, which means it's no longer available. See, it has to choose. It literally can't do both. And here's the thing. Since those network partitions are absolutely 100% guaranteed to happen in any real-world system, partition tolerance isn't really an option. It's mandatory. You have to plan for it. So the CAP theorem isn't really about choosing 2 out of 3. In practice, it's about this. When a partition happens, which one are you willing to sacrifice? Do you throw consistency out the window, or do you sacrifice availability?
So Section 3, CP versus AP in action. Because every system has to make this choice, it's led to 2 completely different ways of thinking about how to build big distributed systems. You're either building a CP system or an AP system.
And this table just lays it all out so clearly. You've got your CP systems that's consistent and partition tolerant. Their main priority? Correctness above everything else. They would rather just stop working than give you the wrong answer. Then you have AP systems, available and partition tolerant. Their philosophy is simple. Never, ever deny a request. They'd rather give you data that's a little bit old than not respond at all. It's a classic battle, correctness versus uptime.
So let's talk CP systems. Think about your bank account. I mean, would you rather get an error message for a minute or see that your balance is completely wrong and maybe a payment went through twice? Yeah, me too. I'll take the error message. That's a classic CP system. They prioritize consistency. Technologies like CockroachDB are designed specifically for this. They use these clever consensus protocols to make sure that if one part of the system gets isolated, it just shuts down that part to prevent any possibility of bad data getting out.
But now, let's flip it. Let's talk about AP systems. Think about your social media feed. Is it the end of the world if you see a post from 10 seconds ago instead of 1 second ago? Of course not. It's way better than seeing a big, ugly error page. Same goes for a shopping cart. You add an item and it shows up. Maybe it takes a couple seconds to sync across all their servers, but who cares? The system is available. Databases like Cassandra are masters at this. They're built to just say yes to your request and then figure out how to resolve any conflicts later on.
Okay, section 4. It's a spectrum, not a switch. Now, it's really tempting to think of this as a simple choice, right? You're either CP or you're AP. But the truth is, modern systems are way more nuanced than that. It's not a light switch, it's more like a whole spectrum of trade-offs.
And that's what leads us to a newer idea, something called the Paxi-LC theorem. You can think of it as an extension of CAP. It takes the original theorem and asks a really smart follow-up question. Okay, we know what to do when there's a partition, but what about the rest of the time, when everything's running smoothly? So what Paxi-LC tells us is that even when there's no partition, you still have to make a trade-off. The first part is just CAP. If there's a partition, you choose between availability and consistency. But then it adds the else part. Else, meaning in normal operation, you have to choose between latency and consistency. Think about it. Do you want your system to be incredibly fast, even if it means the data might be a tiny bit stale? Or do you want it to be perfectly consistent, which always means adding a little bit of a delay to wait for all the computers to get in sync?
And this is where things get really wild. You have systems on the absolute cutting edge, like Google's Spanner. Technically, it's a CP system, but what they've done is just mind-blowing. They use things like atomic clocks and GPS receivers in their data centers to get the time synchronized down to an impossibly small fraction of a second. The window where things could be inconsistent is so tiny, just a few milliseconds, that it practically disappears. It's so good it almost feels like they've broken the theorem, giving you the best of both worlds.
So, when you boil it all down, what does this really mean? The CAP theorem isn't some bug that we're trying to fix. It's a fundamental law of our distributed world, like gravity. You don't break it, you design around it. It forces every engineer to ask the most important question: what does this application really need? Is perfect ironclad correctness the #1 goal? Or is it being online no matter what? And the answer to that question, well, that defines pretty much every digital service we use every single day.